I am coming close to finishing composition of part 1 of the exam with which you deal tomorrow evening. As I told you before, a good portion of part 1 will require you to demonstrate understanding of chemistry. Carbonate ion, oxalate ion. There's a structural formula version of oxalate ion. And chemistry of the other material forms of these ions. Of course, that's hydrogen carbonate ion and hydrogen oxalate ion. And hydrated CO2, or true carbonic acid, and oxalic acid itself. The formulas for these materials, except for true carbonic acid, all appear in our acid-base table. Now, true carbonic acid and hydrated CO2 have the same formula. Compositionally, they're the same. But structurally, they're not. I'd say at least 60% of earnable credit from part 1 has to do with what I just reminded you about. Acid-base chemistry. Lewis acid-base, Bronsted-Lowry acid-base chemistry. Lewis acid-base chemistry. That involves precipitate formation. Buffer solutions. Fundamental thermodynamic considerations. These are all fundamental thermodynamic considerations. I've decided to conclude part 1 by adding some questions on electrochemistry. So part 1 from a content standpoint will be essentially review up through and including chapter 22, because that's the electrochemistry chapter. Whatever I wish to ask you about regarding stuff we have not yet asked you about on exams, like rationalizing strengths of Bronsted acids, bases, stuff like that, that's chapter 23 stuff. And the stuff we're presently considering, chapter 24 stuff, that'll be on part 2 of the last exam. Part 2 again is Tuesday evening. The location will be not CLB 130, I forget where it is, but I'll tell you on Monday as well as Tuesday. Keep in mind you have discussion class gathering tomorrow. Be there. Also, as I've already reminded you, now I'm reminding you again, bonus quiz 3 is due Monday morning right here at the start of class. Along with bonus quiz 3, I shall expect you to submit one of these forms completed in behalf of your discussion instructor. It will be Lynn Pham, for those of you who lit Pham, Tu Win, for those of you who have been with Tu, and Aya and Morgan. So really, those of you who have been with Aya and Morgan should have 2 of these. So you can say something about Aya and say something about Morgan. How many of you with Aya and Morgan? Let's give you some more of these. I don't think it's overburdening. Aya, Morgan? Any more Aya, Morgan?
Dr. Amanda, just a question. Formula you have for oxalate.
What about it?
With the charges written out.
With the charges written out. These both have charges.
Yeah, but I'm saying that's C303.
What is that?
That's the wrong two.
The 2 on the C should be on the Yeah, the two should be.
No.
What is that?
On the second C, put subscript 2, and that should be on the.
Oh.
No.
No,
that too.
No, this is all right. I see what I got. Okay, now we got it. Wonderful. Good. That's good that you noticed that, because I didn't. It's too close to it. That better? Now, let's get back to isomer consideration for transition metal complexes. We talked about geometric isomerism as well as optical isomerism, which are the two subcategories of stereoisomerism. Showed examples of each yesterday. But the examples we showed included exclusively monodentate ligands. For example, for the cobalt complexes which we considered, we had 6 ligands in the first coordination sphere, because the complexes we looked at were octahedral, given that octahedral is by far the most common complex geometry shown by, or most common geometry shown by transition metal complexes, octahedral. Now, what about this formula? How can I draw a picture of this stuff? Well, I remind you, given that you were introduced to this stuff last Friday, this is ethylene diamine. Diamine refers to the 2 amino groups, one at either end of the molecule. Ethylene has to do with the fact that the central carbon atom component of this stuff is an ethylene group. I don't care about the names. The formula is what counts the most. So with the Lewis structure for this, you see the non-bonding pairs. If you want to write them like this, that's all right. Just to remind you for sure that you recognize these as non-bonding pairs. One non-bonding pair each on each terminal nitrogen atom, which makes this a bidentate ligand, which makes this capable of simultaneously forming 2 coordinate covalent bonds to the same transition metal ion. And we showed you a nice Easter hat, which you can get if this thing simultaneously coordinates the same transition metal ion. Gives you a 5-atom ring. We'll talk about the stability of a 5-atom ring versus a 4-atom ring, 3-atom ring, 6-atom ring in a short while. This happens to form a 5-atom ring, which is quite stable. And remind you also that this can coordinate 2 cis coordination positions in an octahedron, not trans coordination positions. So if ethylene diamine coordinates to this octahedron, an ethylene diamine molecule can go here, 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 and here. But it can't go here to here, and it can't go here to here, and it can't go here to here. Those are trans coordination positions. Why not? On what basis can you realize that these bidentate ligands do not simultaneously coordinate trans coordination positions in, for example, the first coordination sphere of an octahedral complex?
Does it have to do with the coordinate covalent sites being inside the molecule instead of on the periphery?
Inside the molecule. I don't know what you mean by inside the molecule.
Like they're not outside.
What do you mean by outside?
Never mind.
Well, let's see here. In this case, never mind the ligands themselves. Just recognize that the ligands are composed of atoms. And atoms are material entities. Nothing fancy about this statement. So if I have an octahedral complex, all these coordination positions are filled. There's a ligand donor atom at each and every one of these coordination positions, of which there are 6 for the octahedral complex. Or at least a complex which is 6 coordinate and shows a geometry which is close to being a perfect octahedron. Well, if I have ethylene diamine connected to this coordination position with one of its nitrogen donor atoms, then we've reminded you that this ethylene diamine ligand could simultaneously coordinate to this coordination position with the second nitrogen atom. Or here, or here, or here, but not here. Number 1, because it's too short. But more importantly, because I can make the carbon skeleton longer. More importantly, these other ligands are material entities. And remember, these sticks are only here to show you where the bond sites are. These atoms are really snuggled right up into the valence electron cloud of the central atom. Well, that's going to prevent the skeletal atoms of ethylene diamine from interconnecting this coordination position with one nitrogen atom to this coordination position with the second nitrogen atom, because the skeletal atoms of the ligand are going to be sterically blocked by the ligand atoms that are in this square plane. It's a steric hindrance problem. You can't have 2 atoms in the same space that's occupiable only by 1 atom. So, and you likely have noticed this on the bonus quiz, we ask you to recognize that these polydentate ligands, this is simply bidentate. We could have tridentate, tetradentate, pentadentate, even hexadentate. But any ring structure, because you always make a ring structure when a polydentate ligand does its coordination thing. Always make a ring structure. The ring structure will always connect cis coordination positions and not connect trans coordination position, mainly because of steric hindrance. Speaking of hexadentate, in looking at the information in the notes, did you perchance take a peek at the information on the notes on this very special hexadentate ligand? You know what this stands for? Have you seen this before? Have you heard of it? EDTA. Sound familiar? Regarding household cleaning products, this is an ingredient in many common household cleaning products. Common bathroom scum, particularly in Florida. Carbonate deposits, phosphate deposits. Materials which are not very soluble in water at all. So if you have carbonate or phosphate scums that you want to clean, water hardly does the job. But if you have a water solution containing ethylene diamine tetraacetate anion, which is this stuff, then you can get that stuff to dissolve by complexing the metal ion component of the scum, like calcium ion and calcium carbonate, or calcium phosphate, or calcium sulfate, or iron ion in ferric carbonate or ferrous carbonate. And there are other things. ethylene diamine. Ethylene diamine, tetraacetate anion. What we do is to go to the laboratory with the ethylene diamine molecule and do chemistry, which involves replacement of each hydrogen atom with an aceto group. Aceto group sound like something you might be familiar with? Aceto group. What's this? We've talked about this before. The acetate ion. What we do in the laboratory to make ethylene diamine tetraacetate anion is to replace one of these hydrogen atoms on this CH3 group that's part of the acetate ion while replacing one of these hydrogen atoms with that. So you wind up knocking off hydrogen and bonding to it this aceto group. Here's N. You knock off the other hydrogen, put on another aceto group. Another hydrogen, another aceto group, another hydrogen, another aceto group. That's where you get the tetraacetate anion. So you got another one of these to one end nitrogen. Then you got CH2, and a nitrogen, which has also got two of these. So this is a big ion. And now look at how many donor sites you have. Because you've turned this molecule into that ion. So you still have this nitrogen donor atom, you still have this nitrogen donor atom. You think this can be a liganding portion also of this EDTA we're making? Got negative charge density here? So this can be a coordinating site also. Now, based on the chemistry we've done, you add 4 of these to one ethylene diamine molecule to make EDTA. So you now have made an ion which can behave in hexadentate capacity. You make simultaneously 6 coordinate covalent bonds with one of these anions to a given metal atom or ion. And that's a way by which you can dissolve bathtub scum, carbonate phosphate deposits. In any case, again, only cis coordination positions occupiable. We've talked about why. And now let's take a look at this complex. Because for an effect which we are yet to discuss, but we will shortly, you'll find out if I take a complex like this, hexamine cobalt 3, a perfectly octahedral complex. Very stable octahedral complex because these ammonia molecules are good, strong ligands. Okay? If I make a water solution of this stuff and treat that water solution with excess ethylene diamine, I will replace all the ammonia molecules in the first coordination sphere of this and turn it into this, for which we have the formula written over here, and here a structural representation of this complex ion over here, or over here. Now again, we're going to talk about this at length a few minutes from now. We want to write an equation for this. Per mole of this 3 moles of ethylene diamine gives you 1 mole of this, and 6 moles of ammonia molecules go in the solution. A reaction like this is known as a chelate effect reaction, because it takes this complex, which strictly has monodentate ligands, and turns it into this, which is a chelate complex. Because when these multidentate ligands do their thing, we get ring structures. They're called chelate complexes. Chelate comes from the Greek word chelos for claw. Claw. Donor site, metal atom. Bites on it. Makes a ring structure on making this bite. What do you think is the thermodynamic driving force for this reaction? Delta H, delta S, or both? Hexamine cobalt 3, dissolved in water, treated with ethylene diamine. Ethylene diamine replaces the ammonia molecules in the first coordination sphere, making this tris. That's nomenclature. When we have chelate complexes, we change the nomenclature. I don't care about the nomenclature. I'm not responsible for that. This means tris, for 3 chelate rings in this complex. So these chelating ligands, because they're multidentate, have kicked out the monodentate ligands to make this stuff. And you'll find out, we'll talk about this in a moment, that K for this is an enormously huge value. That means it's very thermodynamically favorable, this reaction. Well, do you think then that delta G0 is very large and minus for this reaction, a very spontaneous reaction, that delta G0 is caused to be very large and minus because of delta H or delta S, or both? Well, here's ethylene diamine. Here's ammonia. How do you think the Lewis base strength of this compares to the Lewis base strength of this?
It's weaker in...
When you say it, I don't know what it is.
Ammonia is weaker because it has more S character and it can stabilize charged in.
Wait a minute.
As well.
How's this N atom hybridized?
SP3 is the same.
And SP3.
Yeah.
And this is SP3. So we've got N atoms as the donors. They're each SP3 hybridized. The ammonia molecule has got 3 NH bonds. The nitrogen donor atom in ethylene diamine has got 2 NH bonds. The only difference being a single NC bond versus an NH bond. That's the only difference between these 2 donor atoms. You think that leads to much difference in their valence electron environment? How do you think these compare from a donor strength standpoint? Close? Got your acid-base table? Look at it. While you're looking at it, I'll make a statement. The complex forming ability, the liganding ability of a ligand can often be assessed by its Bronsted base strength. If The donor atom, or the ligand which contains the donor atom, is not a pi bonder. This can't pi bond. This can't pi bond. We're not going to do MO analysis to prove that. So I'll ask that you just accept my statement that these are not capable of pi bond formation. Consequence, since we've recognized the great similarity between the nitrogen donors from ammonia versus ethylene diamine, we can get a good handle on their donor ability by looking at their Bronsted base strength. That's why I asked you to look at the acid-base table. How do these compare as Bronsted bases? You looking at the acid-base table? They're pretty close in strength? They're damn close in strength. See where they are on the acid-base table? Kb ammonia, 1.8 times 10 to the minus 5. It's about 2 times 10 to the minus 5. We'll be writing this down in a moment. Kb ethylene diamine, which you can determine from the information on the acid-base table, is about 8 times 10 to the minus 5. About the same. Not much difference. So, do you expect the very large negative delta G0 for this reaction? To be caused by delta H0 or delta S0? Are we changing bond strengths, coordinate covalent bond strength significantly when I replace the ammonia molecules with ethylene diamine? We've just found out that donor strength-wise, these molecules are very much the same. Well then, that tells us that this is or this is not the reason why delta G0 is very large and minus. Does not tell us. Well, then it must be this. Now, if I run this reaction on a per mole basis, you know, a mole's an Avogadro's number. I start with an Avogadro's number of these in solution and 3 Avogadro numbers of these in solution. Is that a lot of particles? That's 4 times 6.02 times 10 to the 23rd. That's one hell of a lot of particles. Well, look what I wound up with. A mole of this. A mole of this became a mole of this. But when these bidentate ligands attack this first coordination sphere, per bidentate ligand which gets coordinated, I put 2 monodentate ligands in solution. So I am on a mole basis reacting 4 moles of particles, but I'm winding up with 7 moles of particles. You think delta S might say, whoopee, I like this? Are we increasing substantially particle count in the system by this reaction? You betcha. Delta S0 is enormously plus for this thing. It's called the chelate effect. Again, it's called the chelate effect because it involves chelate ring formation. Turn the monodentate complex into a complex where we just have chelate rings. More on this in a moment. Now then, back to the issue of optical isomerism. Here is a picture of cobalt complexed with 3 ethylene diamines. So I got 3 chelate rings. One here, one here, one here. Here is a mirror image of this model. The yellow thing in the middle is cobalt. Here's the chelate ring. The green parts simulate the CH2 part of ethylene diamine, and the white part simulates the NH2 part. NH2, CH2. And I'm not going to put all the atoms in there because it makes the model awfully clumsy and difficult to envision. Okay? So, based on the way I've drawn the picture of this complex on the board, we can see that if I hold a model like this, This chelate ring entirely is in the square plane. This canted square. The equatorial for the octahedral complex. All right. And this chelate ring connects the bottom coordination position of the octahedron to this coordinate covalent bond site, which is also part of this square plane. Whereas this top chelate ring connects the top coordination position of the octahedron to this remaining part of this canted square in the equator of the octahedral complex. Question is, regarding optical character, are these pictures equivalent? Or are they different? Well, we have already reminded you the test you have to apply to answer the question. The test is called superimposability. So, if you have this thing drawn on your paper, then you have to take this here and here and rotate it 180 degrees. That means, among other things, that you're going to take this in-plane chelate ring, which is presently aiming that way, and turn it that way. Okay? And that's a game you have to play on the board. All right? Let's play it on the board. Let's take this one. When you do this, it means I've subjected this to a 180-degree rotation. Okay? Now again, to do the rotation, you're holding the complex by the top coordination position and the bottom coordination position. So those positions don't change when you do this rotation. What changes? The in-plane coordination positions. This one goes here, this one goes here, and etc., etc. If you have trouble visualizing this when you draw pictures on your paper, you can make a very cheap modular representation of an octahedral complex with a piece of paper folded in the shape of a square. And if you want, you can label the corners A, B, C, D. Label the corners whatever you want. Okay? And then, through the center of your piece of paper, take a pen or a pencil and poke a hole in that thing. And you can rotate it. It's cheap, it's crude, but it works. Okay? So, if this is B, which is the way I've got it labeled here, okay? When I do this 180-degree rotation, the B is, if I got it like this, the B is aiming at you. Now I'm going to turn 180 degrees, the B aims at me. Okay? And then you can look and see where these in-plane positions are now present after the 180-degree rotation. So, if I got this like this and I got a chelate ring here, and I rotate this 180 degrees, well, this chelate ring is going to wind up over here. No, here. Crude, simple device. I think you can afford to take a piece of paper and fold it in the shape of a square, and poke a hole through it with your pen or pencil, and play this game if you want to. All right? Now, I think it's ever so obvious that when I play this game, this chelate ring winds up over here. So it's just like this chelate ring. Okay? But what happens to this chelate ring? Well, it's connecting the top coordination position, but it's connecting the top coordination position in this sketch to this back left rear corner of my equatorial of my square that's in the equatorial plane. Well, that winds up over here. Similarly, this coordination position stays the same, but in this sketch, this coordination position is connecting to this coordination position. That coordination position winds up over here after I do the 180-degree rotation. So if I take this and apply the 180-degree rotation, which we consider, it winds up like this. Okay. Let's see what we got here. See this model? Chelate ring aiming that way. See this model? Chelate ring aiming that way. All right? Chelate ring sketch on the board. Top coordination position connected to this back left rear corner of my equatorial square. Right over here. And the bottom chelate ring, this one, connects the bottom coordination position to this front left corner, right here, of the square in the equatorial plane. I'm going to rotate this 180 degrees, just like I did on the board. I'm going to hold this here and here. And the only thing I really got to focus my attention on to see that I do this properly is to remember that this square is going to wind up aiming at me. Now it's aiming there, so I got to turn it like this here, and now it's aiming at me. So here's what I've drawn on the board. Okay? See? The top coordination position is still here, but that connects now this position on the square in the equatorial plane. Here it is, right here. And the bottom ring, after this rotation, now connects this coordination position to this coordination position. Here it is. Here's the bottom chelate ring. Coordination position at the bottom of the octahedron. It comes back to the square in the equatorial plane. That's away from you, the viewer. Over here. So when I look at this picture, and I look at this picture, I can see at a glance these things are different. Point, this complex. Oh, I erased its formula. Here it is. This thing. This is optically active. Its mirror image is in fact something different. Well, now I happen to have another model. Never mind the fact that I don't have this one made out of green stuff. We can live with that. All right? We'll orient this model so that this in-plane chelate ring is aiming that way. So I orient this model so that the chelate, in-plane chelate ring is aiming right at it. Because if our mirror's here, when I show this to the mirror, here's what I see. Or if I show this to the mirror, that's what I see. These are mirror images of each other. And they are different. We've proven on the board with the superposition test. This fails the superposition test because these are not superimposable. We can now do it with the models. I'll overlay. You can see I can overlay these in-plane chelate rings. But I can't overlay the top and bottom chelate rings because this chelate ring aims that way on one complex and the chelate ring, the top chelate ring on the other complex aims that way. Not superimposable. That's what we did on the board. Okay? So with that, let's take a look at a couple more examples just to give you more practice with this stuff. We're going to page 2413 in the notes. We've already done 2417. We finished 2416. And now let's take a look at 2418 and 2419. 2418, example, only monodentate ligands. 2419, we have an ethylene diamine ligand. So the present considerations will apply to the complex you're asked to consider in question 2419. In short order fashion, we can refer to the complex for question 2418 with what I have on the board. 3 monodentate ligands of one type, 2 monodentate ligands of a second type, and a third monodentate ligand of which there's only one, but it's different from the other monodentate ligands. The question is, how many geometric isomers and are any of these optically active? Well, let's draw pictures. Now, I would suggest that when you sit down and draw pictures of something like this, given that we only have a single C monodentate ligand, for every picture you draw, because everyone's going to be looking like this, right? Keep C in the same place. If you start moving C around, you're going to get yourself confused. All right? Because again, every coordination position on an octahedron, because of its great symmetry, is geometrically equivalent to the other coordination positions. I'll put C over here. It doesn't matter where you put it. Just put it in the same place. You likely have already noticed on the bonus quiz that for the sketches I've asked you to draw, the ethylene diamine chelate ring, I believe, you were directed to keep in plane and in the same position for each sketch, or some such a thing as that. Just trying to make your life easier regarding learning how to play the draw picture game. Okay. Now then, for the B ligands, geometrically speaking, how can they be arranged in the complex with respect to each other? Cis or trans. Nothing fancy about that. Okay? Well, then by default, the 3A ligands are now arranged with respect to each other meridionally. Notice that for this sketch, where the B ligands are now trans, the A ligands are still arranged meridionally. Okay so far? 2 A's trans and other A's cis. 2 A's trans, other A's cis. Is there any other possible geometric isomer for this thing? What is the other one?
The A's facially?
All the A's will be facial with respect to each other. Where can I put all the A's and have them all facial? I can put here, here, and here. I can put here, here, and here. I can put here, here, and here. I can put the 3 A's any place except here and here or here and here. Because if I put 2 of the A's here and here or here and here, then I've reproduced one of these sketches. because that would have A's trans as well as cis. The A's would still be meridionally arranged. So, I'll put A here, and A here. Which means that for this third geometric isomer, the B's are cis rather than trans. Now then, if you think there are other possibilities for geometric isomers shown for this complex, what will you do to find out? You'll draw pictures. And if you draw any pictures other than the three we have, you'll find out that this fourth picture you drew has got to be one of these. Because there are no other geometric isomeric possibilities for this thing. But you need to do the practice. Tell me, which of these three is least symmetric? Because now we're asking the question, are any of these optically active? Which of these is least symmetric? Because we've reminded ourselves that if, for example, an octahedral complex is optically active, it's got to be the least symmetric complex.
The third one.
Do we all agree this is the least symmetric? Because here, I've got the B's trans and canceling each other at the middle. A's trans canceling each other at the middle. Here, the A's are still canceling each other in the middle. The B's are not. So, with respect to symmetry, this is the most symmetric of these three because of the A and B trans coordination positions. This is number 2, and that's least symmetric because here no set of like ligands is trans. So this is the least symmetric. Therefore, if any of these three is optically active, it's got to be this one. Well, how do we find out? We play picture drawing games. A, B. A closest to the mirror, C closest to the mirror. A, B. All right? The question then becomes, is this thing the same as this thing? Well, to find out, we're now going to do some rotation investigations. I'll take this one or this one. It doesn't make any difference because we're going to find out they're the same. And rotate. I'll rotate this one. The question is, let's take this out. Put in rotate. To rotate this, to show that it's the same as this, what rotation would you like to perform? To rotate this, to show that it's the same as this, what rotation would you like to perform? For starters, I ask that you focus on C. Because if I'm going to show that this thing is the same as this thing, I've got to draw a picture over here where C is over here. Okay so far? Because here's C on this picture, and I'm trying to show you that this picture is the same as this picture. All right? Now, what rotation operation can I perform on this to put C over there? As C migrates from here to here, how many degrees of rotation is that? What is it? This look like what we got? Three green ones, all cis. Facial. One white one, different from the others, which would be C in this picture, and two purple ones, the B's here. Okay? If I'm going to do a rotation to try to show you that this picture is the same as this picture, and this is the picture I'm going to rotate, what rotation operation do I do on this to put C over here? Okay? Here for this picture, C's over there. Well, I do this. How many degrees of rotation is that? 90 degrees. Good. So C came here. Where did this B go? Here? When you say on top, I mean this is top. You got to be careful about this. This thing is perpendicular to you, okay? B goes over here, A stayed here, B went here, A went over there, and this A went over there, okay? Is this the same as this? Doesn't look like it, does it? No? All right. So I got to do another rotation.
To be rotated on a different axis.
Well, what is this different axis?
The A and B and one right.
Oh, wait a minute. Remember, if I'm going to show you, because this is this, okay? So we get this out of the way now, okay? We're trying to show you that this is the same as this. Okay so far? And I got to keep C here. I can't move C from that position. So what other rotation can I perform while keeping C in this position? Here's the model. If I do any more rotations like this, I got a problem because C goes away from this position. So I've got to do something like this. How about that? See? Because an octahedron really has three main axes of rotation. I can rotate along this axis. I can rotate this way. Okay? Or I can rotate this way. All right? Wonderful. So, here's C. Now the green ones by default are A's. Okay? So this thing that I am holding in my hand, if these are identical, this thing has got to be one of these. It's got to be both of them. Well, let's see how it could be. Here we got A, this way. Up. Up. Okay. A. Here's C over here, and there's B, and there's B. Okay? I mean, if you want, I'll change them to green and white and purple and all that stuff, so they match the colors. So this orientation of this model shows you this is the same as this. There. Green, 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 purple, purple, white, white, purple, purple, green, green, green. So we're agreeing with the model, all right? So we've now shown you with the model, clearly this is this. The question then becomes, how do I rotate this to show you that it's the same thing as this, or vice versa, how do I rotate this to show you it's the same thing as that? All right? Well, the white one's over there, so I'm going to just start by doing this, all right? Now notice, if I rotate this way, now I got a green up top, and a green over there, and a green over there. Here's white. Green, 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 and here's purple, and here's purple. There it is. Okay? So what is the rotation I did? Let's go back. All right? Here's this thing. White, purple, purple, green, 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 green. This is this, okay? Now, when I go from that picture to that picture, the whites are in the same place. What's different is the apparent position of purples and greens. But I got to, when I rotate this, I got to keep this here. Otherwise, I'm going to have white someplace else. So, I'm going to rotate like this. How many degrees did I rotate? 90 degrees. And when I did that, green's up top, green's over there, purple's down the bottom, and purple's back behind the square. That's it. So you see what you've got to do to practice. Now, one remaining consideration for this stuff, and that is 2419. 2419 ethylene diamine, 1 chelate ring, well, let's go G2 and P2 for 2 greens and 2 purple monodentate ligands. All right? Now, directive. For all the pictures I'm going to draw of an octahedral complex, if and when the octahedral complex contains 1 chelate ring, like this one, keep the chelate ring in the same place. I'm purposely keeping it in this square that's in the equatorial plane. Remember, this thing is perpendicular to you. That's why we got the square canted. All right? Well, what possibilities remain? G's are trans while P's are cis. P's are trans while G's are cis. And G's are cis and P's are cis. Geometrically, that's it. No other possibilities exist. I think at a glance you can recognize this. If I purposely put the chelate ring here, because we can only interconnect 2 cis coordination positions, so it doesn't make any difference which pair of cis coordination positions you connect, but keep the chelate ring in the same place. If the G's become trans, that forces the P's to be cis. If the P's are trans, that forces the G's to be cis. But I can still have this remaining geometric isomer for this stuff where each set of like monodentate ligands are cis. All right? Now, which of these is least symmetric? Is it this, where the G's are trans? This, where the P's are trans? How about this, where all like ligands are cis? Yeah, that's least symmetric. So if any of these is optically active, it's got to be this thing. So we'll play the game. Play the game, mean draw the picture. Mirror reflection, what's the chelate ring over there? G up top, G over here, P over here, P over here. Is this, which is the mirror image of this, is this the same as this? Well, the way to find out is the superimposition test, which we achieve by rotation. Appropriate rotation. Well, for this picture of the complex, the chelate ring is on this side. So I'm going to take this thing, hold it by the top G atom and the bottom P atom, and rotate 180 degrees in plane. So the chelate ring goes over here. The G's and P, top and bottom, actually oriented ligands stay in the same place. This P goes over here, this G goes over here. And now I take a look at this picture, and I compare it to this picture. The chelate rings are identically positioned. The up top G, down below P, down below P. But look at these in plane G and P ligands. Not the same position, are they? Point, this one is optically active. And it shows you, this analysis, that CO, EN, A2, B2 has a lower symmetry than CO, A3, B2, C. These each show 3 geometric isomers. But the isomer of lowest symmetry for this thing is optically active. So this shows 4 stereoisomers, one of which is optical. This only shows 3 geometric isomers, none of which is optical. So this has a lower symmetry than this. All right? Now, in preparation for what we're going to tee off with on Monday, I want you to look at this one. Which will show us an example of the last type of geometric isomerism that we wish to consider. Diastereomers. Okay? Couple quick pictures. Cobalt's in the middle. I'm not going to bother drawing that. And we recognize that when we are creating geometric isomers, which may show the possibility of optical activity, we're always looking for least symmetry, which means cis coordination for like ligands. So AA, BB, and CD. Now I'm going to draw this one. AA, BB, and DC. A positions, identical. B positions, identical. C and D positions, not identical. Are these mirror images of each other? The answer, these are not mirror images of each other. But clearly they are geometric isomers. And they are different geometric isomers. They're not superimposable. These are diastereomers. Diastereomers are geometric isomers which are optically active, but which are not mirror images of each other. So we'll finish by writing that on the board. Diastereomers. Optically active geometric isomers. Which are not mirror images of each other. Okay. Now tomorrow you will continue with some conversation on chapter 24 stuff, and also we'll purposely have some time to be devoted to entertain questions that you may have in preparation for part 1 of the final, which is tomorrow evening. But it's up to you to ask these questions. And then we'll have our discussion staff sharp, clear, and ready to field these questions and provide all the answers to these questions that you may ask. Isn't that right, discussion troopers? Okay.